So we are in LU, this one is supposed to be LU3, yeah, because this one is different course code, which is actually supposed to be the old course. Yeah? So LU3, yeah, so previously we have talked about discrete distribution and continuous distribution, right? So under continuous, we have covered normal distribution. Yeah, remember the bell-shaped curve. And under continuous, another one that we have to cover is sampling distribution and central limit theorem. Okay, and the second topic is confidence interval and t-distribution. Okay, let's have a look at sampling distribution first. So what is sampling distribution? So as the name implies, we know we have come across the term distribution, which means the pattern of the whole data. But now our data consists of samples, because of the name sampling. So that's what it describes. So you imagine that you have the whole data, but each of that is sampled. Okay, so if you see this one, the whole thing over here, this is your whole data. Imagine you have the data could be anything, data of weight, data of height, data of marks. Okay, but let's say marks. So you have many samples in your, let's say, population. The whole thing is population. So sample is the general name. Yeah? It can be, if let's say in the problem, it can be named as school, right? It can be team, anything that describes a flock of data. Okay. So you imagine that you have many samples, like schools, and then you are talking about marks. Your data or your your data are about marks. Okay, so yeah, so the whole distribution, when we talk about the distribution of the whole schools, maybe the whole samples, that is an example of sampling distribution because it consists of many samples. And each of the sample, of course, if you're talking about schools, like every school has students, right? Like maybe depends on how much the data are collected. Let's say you put it like 50 students per school. So every sample has its own students. And when we talk about like sometimes distribution, it doesn't mean that the number of the size of the sample must be the same for all. It could be sometimes maybe school 1 has 49 students, school 2 has 52, and then this one is 51, 56, something like that. Okay, so it can be varied. But how you represent every sample, so you must represent, let's say, 49 students. 49 students have their own marks, for example. And if you want to like represent school A, you must find the mean, isn't it? So every sample is represented by the mean or the average values. Okay, so means that here every sample, so this is the symbol of mean, yeah, mean of every sample. So imagine every sample has its own mean. So if let's say we are talking about means now, so our distribution is called sampling distribution of sample means, because now we are talking about means. Every sample is represented by means. So imagine the values actually it belongs to many people within that sample. Okay, so that's what we have to know. Oops, this one is so. This is better. Okay, so yeah, so properties of sampling distribution. Yeah? Sampling distributions of sample means. So now remember this symbol, the mu. The mu means the population mean. Yeah, population mean. But now we are talking about our population now is represented by sample means. So we can say that the population mean is equal to the mean of the sample means. Okay, I hope you don't get confused with the redundancy of the terms. The mean of the sample means. Okay, so which is represented by X bar. So X is actually the sample. So when you have the bar above it, so that's the average. Okay, so that's the first thing. And then the standard deviation of the sample means is equal to the population standard deviation divided by the square root of n. Okay, now this is standard deviation. This is the general symbol for standard deviation. So when it is without any subscript, this one is subscript. So if let's say it's just the sigma, this one is sigma. So this one is referring to the standard deviation of the population. Okay, so that's understood. But when we talk about sampling distribution of sample means, then we relate with the standard deviation of the sample means, this one. Okay, so it's equal to the sigma divided by square root of n. N is the size of the population. Standard deviation of the sampling distribution of the sample means is called the standard error of the mean. That's another term that you have to take note. Okay, so let's have a look at an example here. The population values 5, 10, 15, 20 are written on slips of paper and put in a hat. 2 slips are randomly selected with replacement. Find the mean, standard deviation, and variance of the population. Okay. So with this one, yeah, the means. This one is actually you just the mu is the average of the whole thing, yeah. But then this one is actually the mu is mu x. So you find the average of this divided by 4. And then for this one is given standard deviation. Standard deviation, I think we have to, this one is the, in the first LU, we have that formula for standard deviation. Okay. Okay. I think this one you refer to the formula, to the formula in LU2, in the early LUs. Yeah? There is a formula for that. Okay, this one is quite straightforward, but what I want to focus on here is graph the program for the population. Okay, this is much okay here. So list all the possible samples of, this is actually the sub questions. Yeah? Right. List all the possible samples of size n equal to 2 and calculate the mean of each. Okay, now you have your data is 5, 10, 15, and 20. So that is your data. Now, the question asks us to list all the possible samples. So meaning to say that within the population, like as I mentioned just now, there are many samples. Okay, many samples. Sample size n equal to 2. So this one, each of that consists of 2 data, which could be any of these 5, 10, 15, or 20. Right? And then how you want to list all the possible samples. So it means that you just go one by one. For example, if let's say the sample consists of 5 and 5. Yeah. So I mean, like, okay, this is actually the possible samples. You list one by 5 and 5, 5 and 10, 5 and 15, 5 and 20. And then 10 and 5. Yeah, you just go match one by one. So that is actually all the possible samples until you finish all the combinations. And here, if you see 10, 5, 10, 10, 10, 15, 10, 20. 15, 5, you start with 15. 15, 5, match with 15, 10, 15, 15, 15, 20. And then finally 20, 5, 20, 10, 20, 15, 20. So once you finish all the combinations, that are all the possible combinations. And if you see here, 25, the orientation, the order of the data matters. Yeah? For example, we have 5, 10, and there are also 10, 5. Okay. So although the values are the same, but the order is different. So you have to consider it as a different combination, different sample. Yeah. So those are the possible samples that can make the population. Okay. And then because of why you just choose 2, because of the question asks n equal to 2. Calculate the mean of each. So every of the sample, okay, now this is all the samples, right? So you have to calculate the mean. The mean is like 5 times 5 is 5 lah. 5 plus 10 divided by 2 is 7.5. So you find the mean for every sample. Okay, so these are the sample means. So this is actually how the sample means are developed. Okay, so the mean of every sample. Now we move a little bit further. Okay, now we have already the sample means. Remember in the first topic of LU3, we talked about probability. Okay, now once you have the values of this one, so you have to so this one is here. So you have to like create another table, right? Let's say the mean of 5, how many, the frequency, what is the frequency? So 5 is 1, okay, 7.5, how many is 7.5? So this one, that's all right. So this 2, so the frequency is 2. So now you create a table and create this one is frequency, how often it occurs. Okay, and the same thing goes for the rest, like 10, how many 10 are there? 1, 2, 3, 3. Okay, so this is the frequency, and then we have to find the total. This is the total n, the total f. So you add up all of this is equal to 3, 3, 6, 6 more 10, 13, 15, 16. Okay, 16 is it? 1, 2, 3, 2, 3, 6, 10, 13, 14. Okay. So the probability, remember the formula is the frequency of that particular point divided by the total n. For example, for this one is 1 over 16 is equal to 0.0625. So that's how we find the probability of every. Here is the sample means. Probability of the sample means. Okay, so because we're talking about the sample means. Okay, so it's actually the introduction of this sample means. Everything else is about the same with what we have covered, and the probability. Okay, this is just how to present the data, how you plot it on the graph. This is what is called histogram, this kind of figure. All right. The second part of this topic is central limit theorem. Okay. So there are 2 rules. Central limit theorem is anything related to theorem is like it comes from a theory, principle, something like that. So it consists of many circumstances. Okay. So the first rule, what is consistent in this theorem? If a sample of size n greater than 30 is taken from a population with any type of distribution that has a mean equal to the population mean and standard deviation which is equal to the standard deviation of the population, the sample means will have a normal distribution. Okay, so means here, remember when I say that any distribution that when the n is greater, when the n is big, which is like about more than 25 or 30, okay, but in this case it's 30. So it will have a tendency, the distribution will have the tendency to look like a bell-shaped curve. I've mentioned about this many times, right? So it will be like that, where the average data will lie in the middle. So that is what has been observed by statisticians. So they have come up with like whenever the things is more than 30, it will be likely like a bell shape, the distribution, how the patterns of the data. So that is actually included in this theorem. Regardless whether you have any let's say with regardless of the, I mean, like, for example, if you don't have any idea about what actually the distribution is, but the sample means will have that normal distribution. Okay, so that's the first rule of this theorem. The second rule is if the population itself is normally distributed with mean, mu, and standard deviation sigma, the sample means will have a normal distribution for any size n. Okay, this one is obviously like if it is normally distributed, the whole population. So if we talk about sample means, of course, it will follow the population distribution. Okay, so this is directly related, but the first one here is any type of distribution. Yeah? Any type of distribution, but when the n is greater than 30, the sample means will have its normal distribution. Okay, so those are the two rules of central limit theorem. Okay, if a sample of size n less than 30 is taken, and we do not know the type of distribution, then let's say the n is very small, less than 30, like maybe 20, 10. So sometimes it could be bell shaped, sometimes it might not be. You cannot guarantee it to be like the sample means to have the distribution of bell shaped curve. Okay, so yeah, okay. In either case, rule 1 or rule 2, so what you can assume from those two situations, the sampling distribution of the sample means has a mean equal to the population mean. So many means here. Okay, so this is the information that you have to remember. Yeah? If let's say it satisfies rule 1 or rule 2, the sampling distribution of the sample means will have a mean equal to the population. So this is the expression. Yeah, and for the standard deviation of the sample means, it will be equal to the standard deviation of the population divided by the square root of n. And the standard deviation of the sample means is also called standard error of the mean. Okay. Now let's have a look at an example in order to understand how to apply those rules just now. The heights of fully grown magnolia bushes have a mean height of 8 feet and standard deviation of 0.7 feet. Okay, so you digest first this first sentence. The heights of fully grown magnolia bushes. Okay, now we just imagine bushes, bushes. Let's say bushes lah. I don't know how to draw properly. Magnolia. Okay, it's like magnolia is a plant, right? Okay, so let's say you have many plants in that bushes. So bushes here, it refers to the population. So you have to understand every problem carefully and relate what is the population, what is the mean, what are the samples. So yeah, this is bushes. This is what we assume as the population in this problem. Have a mean height of 8 feet and standard deviation of 0.7 feet. So this information is referring to the mean of population and standard deviation of the population. Yeah. So mu is 8 and the standard deviation sigma is the name of the symbol, 0.7, and this is referring to the population. Okay, now 38 bushes are randomly selected from the population. So means that the bushes is a big bushes, and then inside that bush, I don't know, inside that bushes there are sub bushes, something like that, because it says here 38 bushes are randomly selected from the population. So you imagine that there are 38 samples actually, and the mean of each sample is determined. Yeah? The mean of every bush, actually, every sample is determined. Find the mean and standard error of the mean of the sampling distribution. Yeah. So because we have these 38 bushes, that is actually the samples. So now we are talking about the distribution of those samples. So now, if we want to apply, we want to digest the information, we have, here is actually n, isn't it? So n is 38, and which is actually greater than 30. So it satisfies the first rule of central limit theorem, n is greater than 30. So it means that for the sampling distribution, we can assume that the mu, the mean of the sampling distribution is equal to the population mean. So you can equalize it to the 8, because this is the value here. Yeah, that's the first thing. And then the standard, because the question asks what, find the mean and standard error. Standard error is the standard deviation of the sample means, right? Yeah, so that's the mean value. And then the standard deviation is equal to, you just apply the formula just now. Because why you can apply this? Because of it satisfies the central limit theorem. So the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. N is 38. So you got this value. Okay, so that's the two answers. So here the key thing is you have to relate with the central limit theorem. So that's how you can solve and use the formula. The mean of the sampling distribution. This is another. Sama soalan sama. Oh yeah. Sampling distribution is 0.11. Okay. So the next question, if let's say, find a plot at the mean height of the. Oh, okay. So now once you solve this one, another thing that from the central limit theorem is that we assume that the sampling distribution here follows the normal distribution, isn't it? Normal distribution. So why it is important to take note of this? Because we can apply the, we can use actually the standard normal table because of that characteristics. Okay, now the next question, find the probability that the mean height of the 38 bushes is less than 7.8 feet. Siapa? Okay, so now we know that the mean just now is, the mu is 8, right? The mu is 8. And then, bukan, 8, 8. Okay, so when we talk about, this one is referring to the, not the standard yet, it's the normal distribution only. Because you see the mean is not 0. This is normal distribution. Okay, so the values in the middle here is referring to the mean. Okay, so find the probability that the mean height of the 38 bushes is less than 7.8 feet. Okay, so you originally you know that you plot this one. This is actually the mean. Okay, you know the middle value is 8. And then the questions ask you 7.8. So this is actually covering all the 38 samples actually, yeah. Okay, now so less than 7.8. So on the normal curve, we plot it here. So means that you are looking for the region covered by the tile area below than 7.8. Okay. Now you cannot solve it just by using this normal distribution. You have to transform it to the standard normal distribution because you don't have any values in the table. The one in the table is the standard normal one. Okay, so what you have to do is Remember the formula, z equal to x minus mean divided by standard deviation. That is the famous formula for standard normal distribution. Standard normal distribution. Right, means here, all the values here, this is actually x. Yeah, x. So that's why you can see that the mean is non-zero value. So means you have to convert the from x to z. So yeah. So you know that the mean is 8, and then the standard deviation is 0.11. Okay, now when you convert it, so z equal to x is, let's say, 7.8 minus mu is 8, and then 0.11, isn't it? So that gives you the value of minus 1.82. Okay, now you got the z value. So if let's say we want to draw on the standard z distribution, this is standard. The standard z and normal, right? It's the same. Normal and z are the same thing. Distribution, the one that we refer to the table. And because remember, this one just now is just normal. It's not standard normal. Okay, now you got the z value. So here is 0 actually, and here is minus 1.82, right? So this is the region that you are looking for, isn't it? So we apply the symmetry rules. So it means that the area here is the same with the area on the right side on the tail area, referring to the positive value of 1.82, right? So actually we have to look for this area, and how to find for that area. So we go back to the, shall I put it? Z table. Okay. You apply balik lah yang rules of standard set or normal distribution. Yeah? So here 1.82, z equal to 1.82. Let's say find first 1.82. Supposed to be here. 1.82, that's 0.4656. Okay, so that is actually here, isn't it? 0.46, okay, 4656. 4656, okay, that's the area over here. And in order to find the tail area here, is equal to 0.5. You know the total area on one side is 0.5 minus 0.4656, that's equal to 0.0344. 0.0344. So that is the area on the right side, which is actually equal to the left side. So that is actually the area over here. So what is area? Relate the area is the probability, isn't it? Area is probability. So find the probability that the mean height. So actually this is the answer. 0.034. Any questions? So that's how you apply. I mean, first you understand the central limit theorem, right? And then you relate. You use the principles and the formula and then you move to the standard normal, because what the central limit theorem says, that anything that is greater than 30, the sampling distribution actually will follow the normal distribution. So based on that rule, that's how we apply the normal distribution. But remember, we have to convert the x value into z value in order for us to use the table, the standard normal table. And only then we can use the table just now and find the area. Because if, let's say, you are just relying on this part, you cannot find the area because there's no information related to just a typical normal distribution. Okay, so you have to differentiate normal distribution and standard normal distribution. So the one that is based on the table is standard normal distribution. It has been standardized. Yeah, so that's how you can find the z value first time, find the z value, and then find the probability or the area under the curve. Okay, so that's the first question, and I think the second question is just about oh, this one. The average is actually the same thing, but I just keep this because we have another topic that to cover. So you go through on this, but it's just another problem with different values, but you have to apply all these yeah. You have to apply the rules, the related rules. Okay, yeah, I leave it to you to cover this. What else? So first you see you digest the information sample of 50, then it means that it's greater than 30, then you can apply the central limit theorem and then relate to the Z distribution. Okay. Right. So I leave the examples for you to cover by yourself. Okay, now we move to T distribution. Yeah. So then I have to cover because we have so many topics still, so I have to to cover a bit fast. Right. So the next topic is confidence interval and T distribution. So this is under continuous distribution still. Yeah. So just now is sampling distribution and central limit theorem. Right. T distribution and confidence interval. Okay. First, let's have a look at confidence interval first. So whenever you come across the term interval, interval means it should be something that is related to a range from what to what. Okay. So in statistics, we have a confidence interval. It's actually the interval that we are confident with. Sorry, let back with the term. So for example, if let's say you have any data, let's say I do a study on the collection of data. Okay, so let's say I got the distribution, the whole data, which I put it yeah, like this is actually the distribution of the whole data. But the nature of any study, the nature of any data collection is not always perfect. Okay, for example, if let's say I collect the data of the average height of trees in forest A, for example. Okay, I'm measuring the height of every tree, not every tree, like maybe 50 trees in a forest. Okay, I cannot say that my data are accurate, are 100% accurate. I cannot say that. I should allow that there are some errors that I might not realize, or something that can't be avoided. Okay, so meaning to say that any data collection, there must be some allowance for the errors, I can say. Okay, so let's say the whole distribution, I have this, and I should say that, okay, 95% are accurate, but 5% could be some errors. Okay, so if let's say I put 95%, my data are within 95% are true. So that is what is meant by a confidence interval. It means that the interval that consists of the data that can be trusted, something like that. Okay, so I cannot say that my data are 100% correct. So it's not, it doesn't make sense, right? Because we do lots of errors, right? In anything. So confidence intervals are limits or bounds to indicate the range within which the parameter is estimated to be. So you cannot say your confidence interval as 100%. Okay, so it's not logical. So the normal interval used by the statisticians is 95% or 99%. But normally it's 95%. 95% is like makes sense, like 5% is because of the error. So if let's say 95%, so here you imagine the whole distribution, this is 95%, and this is the one in the tail area are some errors, okay, which is 5%. So that is confidence interval, yeah, confidence interval. The 95% confidence interval is calculated in such a way that under repeated sampling, it will contain the true population parameter 95% of the time. So this is what I've mentioned just now. It means that the things that, the true values, is a measure of the confidence you have that the interval contains the true, same thing. Maybe computer, okay. Another values could be 90% or 99%, but 91% is too high sometimes. 99% is too high, 90% and 95. So those are the common confidence interval values used in statistics. Okay, so when we talk about interval, interval means range. So it means that it's from one value to another value. Yeah? For example, if I say the data is between 30 to 70. So this is actually the interval. So the data is between 30 to 70. So it should be from something to something else. So from there is a range. Confidence level is the probability that you are wrong. That's okay. So this one is referring to if let's say your confidence interval is 95%. So if you're talking about the whole distribution, right? So 95% in the middle. Okay. So as I said just now, the one on the tail area are errors, errors, something like errors lah. Okay, so here is what is called confidence level. Let's say the total here is 5%. This is confidence level. So this is just the term that you have to take. Okay? Confidence interval is the range of values. This one. Confidence level is the probability that you are wrong or the error. So why do we need confidence interval? Why we cannot say our data are 100% true? Because of the mistakes or errors done by humans. When we measure something, we cannot be accurate, totally accurate. So sample mean is not a perfect estimate of the population mean. It is going to be either a little bit too high or a little bit too low. So that's why we have to set the limit. For the estimate of mean to be of value, precise. Okay, so the best way is to construct a confidence level. Okay, how are we going to construct a confidence interval for mu? So these are the parameters that we have to know. What's the sample mean? What's the value of Z? What's the standard error of the mean? Okay, let's have a look at the example here. Or later I'll show the example. Let's have a look at this. Confidence interval. Okay, remember that. Excellent. Okay, so this is the formula of the confidence interval. So whenever we talk about we want to represent our data, remember we always represent with mean, right? With mean. So our mean is between this and this. So the value on the left is called lower limit, and the one on the right is upper limit. Yeah. So this one is so the formula is x. There is x bar over here. X bar, which is the mean, minus z multiplied by the standard deviation of the sample means, and this one is plus. On the upper limit is plus. Okay. So this is the formula that you have to remember. Now let's have a look at one example and how to apply what we have understood from the rules. Assume that the standard deviation of SPM verbal scores in the school system is known to be 100. A researcher wishes to estimate the mean SPM verbal score and compute a 95% confidence interval from a random sample of 10 scores. So the 10 scores are given as follows. So we have to find what's the mean SPM verbal score and compute a 95% confidence interval. Yeah, so the information that we have here is standard deviation of in a school system. So this one you see, this one is like referring to the population. Okay, so means that this one is ada bateri. Sekejap touch dia punya pen. Okay, so this one is referring to the standard deviation of the population, which is this symbol, isn't it? 100. Okay, researcher wishes to estimate the mean SPM verbal score and compute 95% confidence interval from a random sample of 10 scores. So it means that you have a population, which is the school, right? And then actually there are many samples, but we're talking about one sample. So random sample, and this one has 10 scores. So the end of this sample is 10. Okay, this particular sample. Estimate the mean of that sample. Okay, the mean of first is the mean of the SPM verbal score. The mean is this one. The mean is like you add up all this stuff. 380 plus 780 divided by 10. Then you get the mean of the sample, right? Which is 530. So that's the mean of the sample. The n is 10. And then how you want to find the standard deviation of the sample. So you apply this one is the standard deviation of the population divided by the square root of 10. This one is this value. Okay, so that's 31.62. Now we need to find what's the 95% confidence interval. So remember the formula just now, this one, this formula. So mu is equal to x minus z, the standard deviation, right? X plus z, the standard deviation of the sample. Okay. So this one is actually this one. Okay. So what we do not know yet is the z value. So we have to solve that. Yeah. So now we have the information of 95%. That is the things that we know. So it means that you assume the distribution is going to be here, 95%. So obviously you know that this one is 2.5% and this one is 2.5%, right? So what we have to find out the z value. So if you relate with the standard normal distribution, let's say we just solve for the one side. Yeah? So here is 2.5% or 0.025, is it? Yeah. So what's the area over here? Over 0.5 minus 2, there. 0.5 minus 0.025. Yeah, so the area here is 0.475. And we have to know what's the z value over here, right? So that is actually the z value that we are looking for. Yeah. So if we refer to the standard normal distribution, the area is inside, right? So 0.475 is this one, isn't it? Okay. Okay. So that's the area, and it refers to the z value of 1.9, 1.96, 1.96, yeah? Okay. Yeah, so the z value that we are looking for is 1.96. Okay, now we're not done yet. So go back to the formula. So I have mentioned about this. So this one is 1.96. Okay, this one is solved. But what is the x value? Yeah, the x value. The x value here is referring to the, oh, sorry, I forgot the symbol. This one, 530. Okay, so this one is 530. So means that you solve the expression, right? The lower limit 530 minus 1.96, the z value, and the standard deviation of the samples, which is the one that you have solved in the beginning, this one. 31.62, you put it into this expression, you got the lower limit, right? And then you solve for the upper limit. So the difference is only minus and plus. The terms are actually similar. So that's how you got the lower and upper limit. And then how you write the confidence interval. So this one is just leave it as it is. Yeah. So the symbol, the mu, the population mean, is between 468.02 and 591.98 on the basis of confidence interval of 95%. Okay, so that is the answer. So it means that what does it mean? If we relate back to the problem, so the problem is about the score, the SPM score, the scores. So the score is between this and this. Yeah, the data. Yeah, based on the 95% confidence interval. That's how you solve it. Yeah, it's very easy actually because the formula is very simple, but it's just that you have to know, you have to solve this one first, yeah, the sample means, and also this one. But the formula is also simple. And you have to solve for the z value, based on what the 95%. If let's say it's 99%, then it will be different, you know, like if let's say 90% or 95%, 99%, so the tell error would be different. Let's say 99%, 99%. So here is going to be 1% divided by 2, that's 0.05% for each of the sites. So that will give you different Z values. Okay, so the answer for confidence interval, it should always be in the form of like this, the range. It should be, you should use this symbol. Yeah, so it should be that. It doesn't have one whole number. It should be this kind of answer range. Okay, so the next question is 99% confidence interval. So you just change the region, right? So the tell area is different. The area, that area will give you different Z value, and it will give you different range. Normally it's wider actually. So this one is 468 and 592. So here the answer is 448. So the dispersion is actually wider because it covers 99% of the data. Okay, so that's confidence interval. I think that's it. Oh, I didn't know. Oh, I did a t-distribution. Absolutely. Okay, wait. What is this one? Okay, that is confidence interval in general. So you have different different situations. The first one, wait. The first case is when the population standard deviation is unknown. Just now is known, is it? Oh, sorry. So just now is the one that we used just now. This one is when the standard deviation is known, right? If you see the example just now, the value of the standard deviation is given in the question. So we know the value of the standard deviation of the population. There is another situation where we do not know the value of the standard deviation of the population. So in that case, what we have to do is we have to use this formula, where it is actually, it's not denoted as sigma, but because of it is just an estimate. It is called just an estimate of the standard error of the mean. Okay. And instead of, in this case, this is the first situation, we use Z. And in the second Z distribution, in the second situation where we do not know the standard deviation of the population, we use, in this case, we use T distribution. So that is when you have to know what is T distribution first. Okay. So when the standard, okay, the T rather than the normal distribution should be used. Okay, so there are two situations. The first one that we covered just now is when the standard deviation of the population is known. Okay, now let's move to the second scenario here, when the standard deviation of the population is not known. How to use the T distribution. But first we have to understand what is T distribution. Yeah? T distribution is used when mu is unknown, and also the standard deviation is also unknown. So that's the use of T distribution. We use the sample standard S to approximate mu, sigma, sorry. Okay, so the T distribution is symmetrical but flatter than the normal distribution. So the shape of the T distribution is still a bell-shaped curve, but in terms of the height of the distribution, it is said to be much flatter than the normal distribution. So if let's say this one is, if you see this one is the Z distribution, flatter means something that is flatter, which is lower than the Z distribution. So this is, that's one of the characteristics of the T distribution. As the sample size gets larger, the T distribution is a good approximation to the normal distribution. The T distribution is lower at the means and higher at the tails. Okay. It is used when, okay, the population standard deviation is unknown and it has to be estimated from the sample. It is used when the sample size is greater than 30 or the population is normal or approximately. So the formula of T, just now we know that the Z formula, but here there is a formula for T. So this is T, the T formula, okay? It's equal to the x bar minus mean divided by S divided by square root of N. And there is also a T distribution table. It's similar, not really similar, but yeah, it has its own table where you have to refer to the critical values or yeah, to the critical values. Okay, various T values. And what you have to know how to use this table is you have to know the degree of freedom, which is equal to n minus 1, and also the upper tail area. Okay, I'll show later how to use it. Okay. So it means that, okay, so this is actually, if you see this plus minus, it's given by the, similar to Z just now, right? So we have this upper limit and lower limit for the T distribution, yeah? So this one is actually refers to this one. Okay, so this is lower limit, upper limit. It's actually the same if we refer back to just now, let's say the Z just now. This one kan? This one. So this one can also be expressed as mu plus minus. Minus is on the left side. X bar minus good job. Yeah. Z X mu minus sorry. Is actually small. Okay. So it's either plus or minus, and this is actually referring to the lower limit and upper limit. Okay? So it's actually the same, but this one is for the T just now. And this is what we call margin of error, or the range, right, actually. Okay. Okay, so the most important part is how to use that formula, how to use that expression. Okay. Let's go directly to the, see, this one, upper limit, lower limit. So this is actually here. Okay? So plus minus is referring to, is either on the left or on the right, minus or plus. Okay. Let's have a look at the example. So that's how you know how to apply that. Yeah? A researcher was interested in estimating the mean reading speed of TESOL graduates and computing the 95% confidence interval. A sample of 6 graduates was taken, and the reading speeds were 200, 240, 300, 410, and 450, and 600. Assuming the samples came from normal distribution, compute the 95% confidence interval. Okay, so what kind of information that we have here? So it's us 95% confidence interval, but we are not given with any information of the population standard deviation. It's not stated, unlike the first problem just now. The first problem that we go through. Okay. Yeah, so this one, yeah. So this one is stated that standard deviation of SPM school system is known to be 100, although it doesn't mention directly standard deviation of population, but we have to understand this problem, and we know that in this case, the whole school here is the population. That's how we know that it is actually referring to the population. Yeah, that one is when the population standard deviation is known, is given. Okay, so the problem that we have now, it doesn't mention anything, so there's no information of it. So from here, you can say that the population standard deviation is unknown. So why it is important to identify this? So only then you know that you have to use T distribution. You have to use the formula related to T rather than Z. Okay. A sample of 6 graduates was taken and the reading speeds were, okay, assuming the samples came from normal distribution, compute the 95% confidence interval. So you can see that the question still asks the same. You are asked to find what's the 95% confidence interval. Yeah, and then this is the sample. Yeah, how to digest the information, how to solve this problem. Yeah? So we have the samples of 6. Okay, then this one you just have to find x bar, just the normal formula, 200 plus 240 plus 300 until 600 divided by 6. Then you get this value. That is the mean of the samples. Yeah? So straightforward. And then what else? Now we have to find what is the SX bar, which is the estimate, right? Sorry, this is the standard deviation of the samples. But now, since we do not know what's the standard deviation of the population, so we have to use this formula rather than mu just now, right? So now first you have to solve S first, and how to solve that S? So this one is the old formula from, I think, the second or the first LU, not the first, the second LU. So this is the general formula of variance. You know, variance and standard deviation is related. So this is variance actually. But you can find the S by finding the square root of S squared. So this one is a formula from the previous LU. So in the exam it will be given, but you have to know that you have to use this formula in order to find the S. Okay. So find S first and then substitute into this, and here is referring to the samples, which is 6. Yeah? So from there you can solve the standard deviation of the samples, which is this one. Okay, you got S x bar as standard deviation, and then in order to use the T table, you have to find a degree of freedom, which is equal to n minus 1. Okay, so n is 6, and 6 minus 1 is 5. Okay? So df is 5. What else? So we are given 95%. So means when you sketch, the things is here, 95%, right? So we know that the tell area will be, this one is going to be 2.5% and 2.5. So what you are looking for actually, you are looking for the range of T actually. So that's why you have to use the T table. T table, okay. So means here the upper tell area is 0.025, because you only consider one. Degree of freedom is 5, right? Okay, right. Okay, now you can find the critical T from the T table. Let's go to the table. Okay, so this is T distribution table. So you have to know degree of freedom and upper tail error in order to use this table. So our values just now, we have 0.025 upper tail area, degree of freedom 5. Okay. So if we refer to this table, 0.025, that's the column, and then 5. Okay, so this is the value that we are looking for. And what is this value? This is the T. T, yeah. Okay, go back to our problem, 2.571. So the T is 2.571. Okay, so keep the value. So why you need the T value? Because you want to solve this expression. Remember, this is the expression for the confidence interval when the standard deviation of the population is unknown. So you have to use this instead of Z. That's all right. So you know what's the X bar values. You already know what's the standard deviation that we have calculated initially. And then you just substitute the T value. Then that's how you solve the lower limit and the upper limit. Yeah, so you got the value for lower limit, upper limit, and how you want to present the final answer. Remember, this one is still the same. You just leave the symbol of mu, the population. So means that the range, the confidence interval is between, the value is between 209.904 and 523.43, based on 95% confidence interval. So actually that's it. You can see the pattern is the same, but it's just that in the middle part is different. Yeah, for two cases. The first one is when the standard deviation of the population is known. We use Z formula, right? Z multiplied by the standard deviation of the sample. But when the standard deviation of the population is unknown, then you have to solve using T. First, you have to solve for the T and then put it into the expression of the lower and upper limit, and we got this confidence interval answer at the end. Okay. Yeah, so in between here, if you see the notes over here, it's a bit like wordy, like actually is, you don't have to worry. This thing is actually is meant by the margin of error. Yeah, but actually the key thing is you have to find this one actually, the confidence interval. Okay, any questions? So that's the two examples. The first example just now, when the standard deviation of the population is known, we use Z, and then when it is unknown, we use T. Okay. So that's what today's topic is all about. So we have covered sampling distribution just now, central limit theorem, and then move to T distribution, confidence interval first, and then we move to the T distribution. Okay. Yeah, any question? If you don't have any questions, that's the end of today's lecture. Okay, if you have any question later on, you can just email me. Okay, maybe you have to do some question first, practice first, then digest the concepts. So only then. So the key thing is you have to digest the problems properly. Find out whether there is, I mean, it's very straightforward. Like if the standard deviation of the population is not given, then obviously you know that it is unknown. So you have to use T distribution. All right. So yeah, thank you for your attention. Yeah, I'll see you guys next week, inshallah.
Sorry, doctor.
Yeah.
I haven't scanned the QR attendance.
Okay. Hold on. Yeah. Okay. The rest will have scan. You ready? Yeah. Have a nice day.
Thank you, doctor.
Thank you,
Welcome.
Doctor.
Welcome.
Thank you, doctor.
Welcome.